These are your notes for Unit 1, Day 4 of Calculus. If you would like to see the warm-up review question or any homework questions we covered in class today, just let me know. So today we're going to talk about continuity and define it. What does it look like? What does it mean if a function is continuous? And we'll talk more about one-sided limits and what they have to do with continuity. So what is continuity? So continuity means that there's no breaks in the graph. You didn't have to pick up your pencil to draw it. So a function that's continuous could be like a polynomial function, right? So like a smooth curve. There's no breaks in that graph. There's no holes, there's no jumps, there's no asymptotes in the graph. It could also look like a piecewise function as long as the pieces connect to each other. So it could have corners and cusps and things like that. So a corner is like a sharp turn in the graph, like an absolute value. And then a cusp is when like a curve meets another curve. So those graphs are continuous. So there's no holes, there's no jumps, and there's no asymptotes in the graph. So as long as none of those things exist, then the graph is going to be continuous everywhere. We can also talk about a graph being continuous just over a given interval. So if you eliminate where it's discontinuous, you can also say that it's continuous on a certain interval. So let's talk about those different types of continuity. So one type of discontinuity would be a hole. So for instance, if we had f of x equals x squared minus 4 over x plus 2, if you remember during our pre-calc review, this is a rational function, and so if I went to graph it, we would have x plus 2, x minus 2 over x plus 2, and those x plus 2's cancel. And remember, in a rational function, where things cancel makes a hole. So we have a hole at x equals negative 2. So now the only thing that's left to graph once we cancel that is f of x equals x minus 2. Well, that's just a line that has a y-intercept at negative 2 and then goes up 1 over 1. And then if I connect those, that's my graph. But it has a hole at negative 2. So at negative 2 on the graph, where x is equal to negative 2, you would just make a little opening there to indicate that it has a hole. What if I wanted to find the height of that hole? Well, the height of the hole is just going to be the limit as x approaches negative 2 of that graph. So the graph doesn't actually exist at negative 2, but if I took the limit there, that would tell me what the height of that hole is. So we factored and we canceled, and so if I plug in negative 2, so this would be x plus 2, x minus 2 over x plus 2. If I plug in negative 2 into what's left, the height of that hole is negative 4. So 1, 2, 3, 4. I'm a little bit off on my graph, but the height of the hole should be at negative 4. So one type of discontinuity is a hole. So there's a break in the graph. Another type of discontinuity is a jump. And jumps occur with piecewise functions. So if we had like x plus 2 if x is less than 0, and then let's say it's x squared if x is greater than or equal to 0. So x plus 2 if x is less than 0. If I plug in 0, I get 2, and it's going to be an open circle. And then if I plug in negative 1, I get 1. And so this is just going to be the graph on the left side of 0. And then it's x squared if x is greater than or equal to 0. Well, that's just a parabola. And we know how to graph a parabola. So it's just that right part of the parabola. So that would be that piecewise function. But notice at x equals 0, there's two different heights at x equals 0. So the limit doesn't exist there. We call that a jump in the graph because the y values are jumping from one value to the next at the same x value. So that's a jump in the graph. You could also have something called an asymptote. So if I just had f of x equals 1 over x plus 2. So remember in our rational parent function, you have a vertical asymptote at x equals 0, but this graph right here, we're moving that asymptote over. So remember, you set the denominator equal to 0, and that's telling you where the vertical asymptote is. So this graph has a vertical asymptote, oops, not at positive 2, at -2. So at x equals -2, there's a vertical asymptote. And then remember, horizontal asymptotes, you play the degree war. The denominator wins. So it has a horizontal asymptote at y equals 0. And then this graph is just going to look like this. So notice there is an asymptote in this graph. So there's a break in this graph where in the middle of the graph, one part of the graph shoots down and another part of the graph shoots up. So when in the middle of your graph, if your graph is shooting up to infinity or down to -infinity, you have an asymptote. So those are the three types of discontinuity that we're going to focus on: holes, jumps, and asymptotes. So one-sided limits and continuity. So for a function to be continuous, we know that the limit as you're approaching that x value from the left has to be the same as you're approaching that x value from the right, right? We need those two heights to be connected, right? So here, the limit would not exist because the two heights are connected. Here, the limit would exist because the two heights are connected at the same y value. So let's talk about this. So if I wanted to look at the limit as x approaches 1 from the left, what's going to be the limit as x approaches 1 from the left? Well, as I'm approaching 1 from the left, the height of that graph is at 0. Well, let's look at the right-hand limit. What's the limit as x is approaching 1 from the right-hand side? Well, as I'm approaching 1 from the right-hand side, the height of that graph is 1. Now notice those are two different values. What is happening on the graph right there? What type of discontinuity is happening there? The limit doesn't exist because it's two different y values. So when your limit from the left and limit from the right are different, there's going to be a jump in the graph. Let's look at what's happening as I'm approaching 2. What's the limit as x approaches 2? Am I approaching the same y value on both sides? I am. I'm approaching a value of 1 on both sides. So my limit exists, but what doesn't exist right there? What's f at 2? Well, f at 2 exists, but where is it? It's up at 2. Notice since the point that exists and the limit that exists are different, it's just an isolated point right there. So the limit exists and the point exists, but since they're not the same, the graph is not continuous there, and it's going to be a hole. And then if your limit is going to infinity or -infinity, then that's going to be an asymptote. So we'll talk about that. So for a function to be continuous at a point, 3 things need to happen. First, the limit as x approaches that x value from the left has to be the same as the limit as x approaches that x value from the right, which means that the limit as x approaches c exists. So the limit has to exist. So for a function to be continuous at a point, the limit has to exist there. Step 2, the y value has to exist there. So f of c exists. So at x equals c, the y value exists. So there's no just hole there. There's an actual point there. The y value exists. And not only that, but whatever the limit is, so whatever height the graph is approaching, has to be that y value. So the limit is the same as the point. So for a function to be continuous at a point, 3 things need to happen. The point needs to exist, the limit needs to exist, and the point and the limit need to have the same value. So for instance, if I were to just graph this, and let's just look at right here. So at x equals 0, is the graph continuous? Well, we would have to look at the limit. What's the limit as x approaches 0 of my graph? Well, the limit is just whatever the height is, and my graph is at a height of 3. So the limit as x approaches 0 is 3. And then you need to look at the y value. What's the y value when x is equal to 0? Well, that's just the point, and again, the point is 3. So are the limit and the point at the same height? They are. Since the limit as x approaches 0 of f of x is equal to f of 0, then the graph is continuous at f equals 0. So the limit has to exist, the point has to exist, and the limit and the point have to have the same value. So let's go ahead and discuss the continuity at these different places. So at f at 0 is 4. f at 2 does not exist. There's no point at f at 2. F at negative 2 doesn't exist because there's an asymptote. The limit as x approaches 2 from the right is going to be, it looks to be about 1/2. The limit as x approaches 2 from the left also looks to be about 1/2. So the limit as x approaches 2, since both the left hand and the right hand limit are both going to 1/2, the limit at x approaches 2 is 1/2. The limit as I approach 0 from the left is going to be 1/2. The limit as I approach 0 from the right, well, that limit's up at 4. So since the limit as I'm approaching 0 is at 2 different values, the limit as I approach 0 does not exist. And then my limit as I approach negative 2 also doesn't exist because on the left side, it's shooting down to negative infinity, and on the right side, it's shooting up to positive infinity. So let's talk about the different types of discontinuities. What's happening at x equals negative 2? What type of discontinuity is that on the graph? Well, that's an asymptote. So notice the limits. One piece of my graph is shooting up to positive infinity, and the other piece is shooting down to negative infinity. So my limit doesn't exist at negative 2, and neither does the y value. So there is a discontinuity in the graph there. What's happening at x equals 0? What type of discontinuity is happening there? Well, that's a jump because the limit doesn't exist. The limit from the left and the limit from the right are different values, so it's a jump in the graph. What's happening at 2? X equals 2. Is the graph continuous at x equals 2? It's not because there's a hole in the graph there. What about at 4? Is the graph continuous at 4? Well, notice both pieces from the left and the right seem to be shooting up to positive infinity. But remember, when the graph is shooting up to a positive infinity or down to negative infinity in the middle of the graph, that means that there's an asymptote on the graph. Even though it's not drawn in, it means that there's an asymptote there. All right, so let's look at some without a graph. So let's talk about the continuity of each of these based on the given x value. So what's happening as I'm going to negative 4 from the right? So remember, the first step on any limit problem is plug in. So if I plug in negative 4, I would get negative 13 over 0. Well, that's sad because I can't tell what's happening. But notice, if I plug in negative 4, that means that I'm going to have a vertical asymptote on the graph at negative 4. So this is a rational function, and it has a vertical asymptote at negative 4. I want to know what's happening as I'm going towards that vertical asymptote from the right. Well, one way to tell algebraically is to pick a number that's close to negative 4, but on the right side of negative 4. So like 3.9, I could plug in. So what happens if I plug in 3.9? So if I took 3.9 and plugged it into the numerator and the denominator, what's going to happen? Well, if I plug 3.9 in the numerator, I get a positive value. And if I plug in 3.9 in the denominator, I also get a positive value. What's a number? So basically, my denominator is going close to 0. So I could think of this as a number over a really small number, so 0.00000001, right? Because if I made that 3.9999999, oh, sorry, negative 4, so negative 3.9999999. So if I plug in negative 3.9999, I'd get a really small number. What happens if you take 1 divided by like a billion? Or sorry, not like a billionth. So 1 divided by 0.000001, you end up getting a huge number. And so you are trying to figure out, is it positive infinity or negative infinity when you do that? Well, since I got a positive over a positive when I plugged in negative 3.99999, this is actually going to be positive infinity. So that means that when my graph is approaching that vertical asymptote from the right, the graph is shooting up to positive infinity. That's what's happening on the graph. So let's look at the next one. It's going to be something similar. So if I plug in 1/2, I would get a number on the top, 4.5. If I plug in 1/2 into the denominator, I get 0. So I get 4.5 over 0. So again, that's undefined. It's not indeterminate. It's undefined. So I know that at 1/2 on my graph, I have a vertical asymptote. I want to know what's happening as I'm approaching that vertical asymptote from the left. Is my graph shooting up to the sky or down to the ground? So we're going to pick a number that's on the left side of 1/2. A number on the left side of 0.5 could be like 0.4. So what happens if I took 0.4 and plugged it in? If I plugged it in the numerator, I'd get a positive answer. If I plugged it in the denominator, 2 times 0.4 minus 1 is negative. So I get a positive over a negative, which is a negative. So that means as I'm approaching the vertical asymptote on the left side, it's going to shoot down to negative infinity. Let's look at the next one. X is approaching 1 from the left-hand side. So if I plug in 1 into the numerator, I get 4. If I plug 1 into the denominator, I get 0. So again, that's undefined, so I want to know what's happening. So at 1, that means I have a vertical asymptote on the graph, and I want to know what's happening as I'm approaching it from, does that look like a positive or a negative? Maybe a positive. So as I'm approaching 1 from the right-hand side. So from on the right-hand side, is my graph going to shoot up or shoot down as I'm approaching 1 on the right-hand side? So I'm going to pick a number close to 1, so like 1.01. And what happens if I plug 1.01 in? Do I get positive or negative overall? Well, the numerator is positive. The denominator is going to be, good question, 1.1. I think it's, well, let's try it on Desmos. So we're going to do 1.01 squared. Oops. 1.01 squared minus 2 times 1.01 plus 1. And it's positive. So I get a positive over a positive. So that means that this graph, as I'm approaching 1 from the right, is going to shoot up to positive infinity. If you guys would like to see this last one worked out, just go ahead and go to the finish notes. So you could try that right now and then go to the finish notes to check the answer. All right, so let's determine if these following statements are true or false. So the limit as x goes to negative 3 from the right doesn't exist. So here's negative 3. As I'm going to negative 3 from the right, do I have a height? I do. So that is a false statement. The limit there is 0. X is going to negative 2 from the right. So here's negative 2. As I'm approaching negative 2 from the right, the limit is negative 1. Nope. It looks to be at a height of negative 2. So that's also false. My limit as I'm approaching 0 from the right. So here's 0. As I'm approaching it from the right, it looks like it's going to go to a height of negative 1. So that is a true statement. The limit as x goes to 0 from the left is 4. Well, as I'm approaching 0 from the left, it looks like it's going to a height of 0, so not 4, so that's false. F at 0 is 4, so at 0, that point is 4, so that is true. As I'm approaching 1 from the left, it doesn't exist. So technically, as I'm approaching 1 from the left, it's going to negative infinity, which is not a real number. So yes, you could say that doesn't exist, or you can say it's negative infinity. All right, let's go ahead and talk about the continuity of each of these functions. So where is the first function discontinuous? Well, it's discontinuous at x equals 1 because what type of discontinuity is that? It's a jump. The second function, where is it discontinuous? Well, it's discontinuous at x equals 5 because what's happening on the graph there? There's a hole on the graph there. So checking rational functions. Well, are rational functions continuous? Well, let's test this out. So where would this function be discontinuous? Well, the denominator can't be 0. So x cannot be negative 2. What happens at negative 2? You have a vertical asymptote. So my graph is discontinuous at x equals negative 2 because there's an asymptote there. So to check rational functions, you're going to look at the denominator and see if the denominator can equal 0. If it can, then you're either going to have a vertical asymptote or a hole there. It's a hole if the numerator and denominator factor and cancel. So to check to see if piecewise functions are continuous, you want to check where they overlap. So we're going to check the overlap. So these two overlap at x equals 2. So for this function to be continuous at x equals 2, when I plug 2 into the top and I plug 2 into the bottom, I need the same y value in both of those cases, right? Because we've talked about this. The limit as x approaches 2 from the left, I'm going to use the top one because those are values of 2 from the left. So if I plug 2 in, I would get 3 minus 2 is 1. And then I need to see what's happening on 2 from the right. So 2 from the right, I'm going to use the bottom function because those are on the right-hand side of 2. And if I plug 2 into that, I get 2. So notice those two limits are different. So the limit as x goes to 2 of f of x does not exist. And if the limit doesn't exist, then it's not continuous. And remember, if those two limits are different, it's a jump. So the function is not continuous at x equals 2. So remember the three things that need to happen for a function to be continuous at a point. The limit has to exist, the point has to exist, and the limit has to equal the point. Well, does the point even exist on this function? We have x is greater than 2 and x is less than 2. X is never equal to 2, so the point's never going to exist on that function anyways. All right, let's look at the next one. So for a rational piecewise function, remember if we want to talk about the limit of a rational, that bottom one is the isolated point. So the point exists, f at 1 exists, and it's 2, so the point exists, so that's good. The limit also has to exist, so we're going to take the limit as x goes to 1 of x squared minus 1 over x minus 1, and if we factor and cancel that, we get x plus 1, x minus 1 over x minus 1. The x minus 1's cancel, and if I plug 1 back in, I get 2. So notice the limit as x approaches 1 is also 2. So the limit exists. The point exists. Are they equal to each other? Yeah, they're both equal to 2. So yes, this function is continuous everywhere, but at x equals 2, it's continuous. All right. Let's find the values of these functions where the function is not continuous. So the first one's rational, so it is not continuous if the denominator equals 0. So x squared plus x plus 1 can't equal 0. Can I multiply to 1 and add to 1? No, so we're going to use the quadratic formula to solve. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Well, watch what happens. We get negative 1 plus or minus the square root of 1 minus 4 over 2. That's going to give me imaginary answers. Since my denominator is never equal to 0, this graph is continuous everywhere. There is no point of discontinuity because the only place where a fraction can be discontinuous is when the denominator is 0. So for the second one, the point exists. F at 0 is equal to 3, so the point exists. And then if x is not 0, so we want the limit as x goes to 0. So remember, for the limit on piecewises, you don't look at the isolated point, you look at the function. So x squared minus 4x plus 3. If I plug 0 into that, I get 3. Are they the same? Are the point and the limit the same? Yes. So since the limit exists, the point exists, and they're equal, f of x is continuous everywhere as well. So removing a discontinuity. How do we remove a discontinuity? So is this function going to be continuous everywhere? So we have x to the third minus 7x minus 6 over x plus 3, x minus 3. So this function is discontinuous at x equals negative 3 and x equals positive 3, right? It would have vertical asymptotes there. So what we would want to do to, well, it's harder to remove a, let's change this to, nope, that wouldn't work. Let's change this numerator, and then I can show you how to remove a discontinuity. So let's change this to x plus 3. So if I change that to x plus 3, then I can remove the discontinuity at x plus 3, because since they canceled, what happens when x plus 3 is equal to 0? Or at x equals negative 3. There's a hole there. You can remove discontinuities when there's a hole. How do we do that? We're going to make it into a piecewise function. So if my original function was x plus 3 over x squared minus 9, so as long as x is not equal to negative 3, I can fill in the hole. To fill in the hole, I need to make a y value. I have to make a point that fills in the hole. So I need to figure out the height of the hole. And remember, to figure out the height of the hole, we find the limit. So what's the limit as x approaches negative 3 of x plus 3 over x squared minus 9? Well, we already factored and canceled x plus 3 over x plus 3, x minus 3. And then remember, if I plug it back in, I get 1 over negative 6. So the height of my hole is negative 1/6. So if I make an isolated point that fills in the hole, so if x is equal to negative 3, if I make the y value negative 1/6, I filled in the hole. So I've removed that discontinuity by filling in the hole. So you can remove discontinuities by filling in holes. So you can fill in the hole and you will remove a discontinuity. You can't remove a jump discontinuity or an asymptote discontinuity though. There's no way to like fill it in with an isolated point. So finding values to make a function continuous. So for a function to be continuous, where the pieces overlap, my function pieces need to be equal. So at x equals -3, I need my two pieces to be equal. So I need 2x minus a to be equal to ax plus 2b. I need those two pieces to be equal. And I also need where the second two pieces overlap, and they overlap at 3, I need those two pieces of the function to be equal because I need their y values to be the same. I need them to be at the same heights. So ax plus 2b, ax plus 2b has to equal b minus 5x. So now what I'm going to do on each of these is I'm going to fill in the x values. So this is going to be 2 times -3 minus a equals a times -3 plus 2b. So this is going to be -6 minus a equals -3a plus 2b. I'm going to get all my a's and b's on the same side. So -6 is going to equal -2a plus 2b. Well, I have two variables left, so I can't solve that yet. So now I'm going to solve the other equation the same way. So I'm going to plug in, this time is when x equals 3, so I'm going to plug in 3 for x. So a times 3 plus 2b equals b minus 5 times 3. So 3a plus 2b equals b minus 15. Get all the a's and the b's on the same side. So 3 plus, subtract the b over. So 3a plus b equals -15. Now notice I have two equations with two variables. I can set up a system and solve this for a and b. So 3a plus b equals -15, and -2a plus 2b equals -6. Well, I'm just going to multiply that first equation by -2, and it's going to become -6a minus 2b equals 30. I'm going to solve using elimination, so I'll add all my pieces. So -8a is going to equal 24. And then if I solve for a is going to be -3. And then plug it back in to solve for b. So I'm going to use 3a plus b equals -15. So -9 plus b equals -15. So b is going to be -6. So if a is equal to -3 and b is equal to -6, if I plug those back in, that would make this function continuous because the pieces would be at the same heights where they overlap. So you guys go ahead and try this one. See what value of a would make this function continuous. You can check your work against the finished notes from class today. So some random properties of continuous functions. If you know two functions are continuous, like if you had f of x is equal to x squared and g of x is equal to the square root of x, both of those functions are continuous. There's no holes, there's no jumps, there's no asymptotes in those functions, so they're continuous. If you were to add them together, x squared plus the square root of x, since both of them by themselves are continuous, their sum would also be continuous. So if I graph that function, there would be no holes, jumps, or asymptotes in that function. Or if you take their difference, x squared minus the square root of x, those functions would also be continuous at that point, x equals c. If you multiplied them, x squared times the square root of x, that function would also be continuous. And if you multiplied either one by a constant, those functions would be continuous. And then also their quotient would be continuous as long as the denominator is not equal to 0 at the given value of x. So those are just some properties of continuous functions. The composition of continuous functions is also true. So if f of x is continuous like x squared, and g of x is also continuous like the square root of x, and then the composition of those functions, f of g of x and g of f of x, both of those functions would also be continuous. So the composition of two continuous functions is also continuous. So if I looked at this ugly guy, I know that sine x is continuous because I know what its graph looks like. I know what x looks like. It's a straight line, so that's continuous. I know what x squared plus 2 looks like. That's a happy parabola that moved 2 up. So that graph is continuous. And I know since if I multiply or divide continuous functions, that the function stays continuous. And now the outside function is the absolute value function. Well, I know the absolute value of x is continuous. It's the v function. So that's a composition of continuous functions. Since each piece by itself is continuous, the whole thing is going to be continuous. All right, gentlemen, your homework is 1.5.